In this video, I want to talk about the idea of linear transformations. And you can think of them as just the linear algebra word for functions between vector spaces. But these functions have to have a particularly nice property. And basically that property says that we can separate things as much as possible inside the function through multiplication of scalars and addition of vectors. So it works very, very nicely. So a little more precisely, the whole idea is that the properties of addition and scalar multiplication still carry over through this function, through this transformation. So let's look at the definition of this. Let's scroll down and talk about this definition. Okay, there we go. So let's have two vector spaces. We'll call them V and W. And we'll say they're over the same field of scalars. And in fact, unless otherwise mentioned, we're saying that they indeed have the same field of scalars when we're talking about two vector spaces. And then we have this function from one vector space V to the other one. We call that a linear transformation, and we abbreviate that as a linear X form for transformation, if and only if the following two things hold. So the first one is that you can either add the vectors in V first and then take the linear transformation of them, or you can take the linear transformation of either vector or of both vectors and then add them together. And a similar thing happens for scalar multiplication. If we have a scalar, we can either scale the vector and then apply the transformation, or we can apply the transformation to the vector and get it in W and then scale it. So either way works. So let's take a look at a few linear transformations here. So here we have a linear transformation, and it goes from the set of n by m matrices, so matrices that have n rows and m columns, and it goes to the set of matrices that have m rows and n columns. And the definition of this transformation is the following. We take a matrix A, so an n by m matrix, and we just take the transpose of it. So just to be clear how this one works, let's say we had the matrix 1, 2, 3, 4, 5, 6, and we apply T to it. Then what we get is 1, 2, 3, 4, 5, 6. So it just takes the transpose of the matrix. So, if you remember from your first linear algebra course, transposition is really nice in that if you add matrices and then take the transpose, it's the same thing as transposing each matrix and then adding it together. So because the transpose behaves like that, we call that behaving linearly. Well, we know that this satisfies the first condition for being a linear transformation. So if we add them and then we apply the transformation, which in this case is the transpose, we get the same thing as if we applied the transformation separately. So we took the transpose of each matrix here separately and then added them together. And the second condition also holds. Scaling behaves very nicely under transposition as well. If we take a scalar, little a, and we multiply it by matrix A, and then we take the transpose, well, remember what happens when you multiply a matrix by a scalar. You just multiply every entry in that matrix by the scalar. So if you take the transpose of it, well, it's all the entries multiplied by that scalar anyway, so you can just factor that out and just keep a transpose, and that's the same thing as taking the transpose of matrix A and multiplying it by your scalar A. Now we'll talk about some common linear transformations that come up all the time. And the first one is basically the do-nothing one. It's called the identity transformation, which is usually represented by the number 1, or you might see it also maybe instead of by the number 1, you might see it by ID. And what it does is it just does nothing. So both the domain and the codomain, so the set of inputs and the possible set of outputs, are the same vector space, and the transformation just takes the vector v and it sends it to itself. So this is called the identity transformation. It just does nothing. Another one that's kind of equally as simple but in a different way is the zero transformation. So this one's called the zero transformation. And what the zero transformation does, it does exactly what one would expect. So it takes any vector from V and it sends it to the zero vector in W. Maybe I'll make that clear here. So this is indeed the zero vector in W, since we're talking about an output of this linear transformation 0. So it takes a vector in V and it maps it to the zero vector in W. That's all it does. That's called the zero transformation. And another one that's fairly common and easy is one that just scales a vector. It's called a scalar transformation. So A is going to be the scalar here, so a lot of times it's written as just the scalar. And what it does is, again, it's like the identity transformation where it goes from a vector space to itself. And it just takes that vector v and it multiplies it by the scalar A. So that's called the scalar transformation. Maybe I'll give a quick example of this one. So if we had, say, let's say that it's, we'll go over R2, I guess. So we'll have 1/2. We'll go from R2 to R2. And then the linear transformation 1/2 of the vector, let's say 6, 4. Well, that's just going to be multiplying 1/2 by this vector 6, 4. So that gives me 1/2 times 6 is 3, and 4 times 1/2 is 2. So it behaves just like scaling. And in fact, we can think about multiplication by a scalar as a linear transformation. And as a little exercise, it might be instructive to check that indeed the two conditions for being a linear transformation are satisfied by scaling. And the nice thing about linear transformations is that they act very, very nicely across pretty much all vectors, but we're going to focus on the zero vector, inverses, so your negatives, and linear combinations of vectors. We're going to show that they behave exactly how you would want them to. So we're going to show the following three things in Theorem 6.1 here. So if we have a linear transformation, then these three things must hold. That the zero vector, and I'll be clear here, if you take the zero vector in V and you apply the transformation to it, because remember, the transformation takes vectors in V and turns them into vectors in W. So if you apply the transformation to the zero vector in V, it must be that you get the zero vector in W. And the second part is if you take the vector negative V and you apply the transformation to it, it's the same thing as if you apply the transformation to V and then took the negative of it. And just to be clear, so negative v here, this is of course an element of the vector space v, and then you apply the transformation to it and you get something in the second vector space w, the target vector space. So here we have that v is of course in v, and if we apply the transformation, then we get this negative t of v, which is in w. And we'll look at some examples, of course, going forward. And the third thing is that if you have a linear combination of vectors, well, you can just take the linear combination of the transformed vectors and then scale them by the same scalars, and you'll get the same thing. So there are the three things we need to show. So the first thing, we want to show that the zero vector in v gets mapped to the zero vector in w. So I know that the zero vector in v, well, I can say that's the same thing as the zero scalar times any vector in v that I like. And now, because I know this is a linear transformation, I can move that scalar outside of it. So this is the same thing as 0 times t of v. And when we were just learning about vector spaces, we learned that 0 times any vector has to be the zero vector. And remember that this t of v, because we took a vector in v and we applied the transformation to it, that lives in w. So now we're in that target vector space, the output vector space. So the zero vector is actually the zero vector in w. So that's great. We know where the zero vector must map. We can do a very similar thing for negatives. So here, I know that negative v is the same thing as negative 1 times v. And we learned that back when we were first learning about vector spaces. And I'm going to do the same thing. I'm going to take that scalar outside. So this is the same thing as negative 1. Oh, let me do this in black, actually. Negative 1 times t of v. And I know that negative 1 times any vector, remember t of v is a vector, but it just is a vector in w now. So negative 1 times that vector is just negative that vector, t of v. So negatives behave nicely. And now let's show that linear combinations behave nicely. Now we're going to do it via something called mathematical induction. If you haven't learned about induction just yet, the basics of it are, well, we're going to show it works when you just have a linear combination of one vector, and then use that knowledge to do it for two vectors, and then knowing that we can do it for two vectors, show we can do it for three vectors, and then knowing we can do it for three vectors, show we can do it for four vectors, etc., all the way up to infinity. And induction is just the formalization of that process. So let's go ahead and do this. So with one vector, well, that's pretty easy. So we have transformation of a1 v1. Well, just by the rule for linear transformations, we're allowed to take scalars outside. So this is the same thing as a times t of v1. So we know we can do it for one vector. Now let's do it for k vectors, whatever k is, for some number k, and we'll show that we can do it for one more vector. So let's assume that we can do it for k vectors, so t of a1v1 plus a2v2 all the way to akvk. So let's say we could do it. So that means that this is going to be a1t of v1 plus a2t of v2 all the way to akt of vk. So we're going to assume that we worked our way up to do it with k vectors, and we need to show we can do it with k plus 1 vectors. So we want to show that t of a1v1 plus all the way up to a k plus 1 v k plus 1 equals that a1t of v1 plus all the way up to a k plus 1 t of v k plus 1. So we want to show we can do it with k plus 1 vectors if we assume we did it with k vectors. So that's going to be our goal here. So what we're going to do is we're going to use the idea of closure of a vector space. We're going to split this up into two vectors. So I know that the linear combination of those vectors there is one vector. And then I have this other vector here. So I'm going to use the linear property of linear transformations to break this up into two transformations. So if I call this, maybe I'll call this whole thing V star, and this thing I'll call V double star. So I can write T of V star plus V double star as T of V star plus T of V double star. And that's just by the linearity of the transformation. Remember, with linear transformations, we can transform either before or after we add the vectors, and we get the same thing. So now, let's look at this T of V star. That's T of this bit. But by our assumption, so by assumption, we know that we can split apart k vectors. So let's go ahead and split that apart. So this equals a1 t of v1 all the way to a k t of vk. That's what we assumed. We assumed we could do it with k vectors. And then we just have this t of a k plus 1 vk plus 1 here, but we can just use the second property of a linear transformation, that we can take scalars outside, to finish this off. So this is the same thing as a t of v1, a1 t of v1 all the way to a k t of vk, and then finally plus a k plus 1 t of v k plus 1. So we've done it. We've shown that if we do have a linear combination of however many vectors, we can use the properties of linearity to be able to split it apart to become a linear combination of the transformed vectors with the same scalars. So that's really neat. So let's look at an example here. We'll scroll down. And this one will be in general, and then maybe after this I'll do another example that's a little more concrete with an actual linear transformation with actual vectors that tell exactly where they go. But for this example, let's say we know we have a linear transformation that goes from a vector space V to a vector space W, whatever they are. And we know the following things. we know T of the linear combination V1 plus 2V2 gives you W1, and 3V1 minus 5V2, if we take the linear combination of that and apply our transformation, we get W2. And we want to know, well, how can we write T of V1 and T of V2 in terms of the vectors W1 and W2? All right, let's give this a go. So let's use our properties of linear transformations to simplify this guy here and this guy here. So we know that from, let's call this, I guess, star, we have that TV1 plus 2 TV2 equals W1. And from double star, we'll do the same thing. We'll use theorem 6.1 to split up this linear combination. So we get that 3t of v1 minus 5t of v2 equals W2. And looking at this should look very familiar to you. This looks a lot like a 2x2 system of equations, really, because it is. And we want to solve for t of v1 and t of v2, so we're treating these like our variables. So if you like, we've transformed this problem into solving a 2x2 system of linear equations. So maybe I'll call t of v1 in this x and t of v2 y. You don't need to do this, but just so it looks more familiar. This is solving something along the lines of x plus 2y equals, still call it w1, but that's just along for the ride, if you will. And 3x minus 5y equals W2. So, if you want, there's loads of ways of solving linear equations. So, I'll leave this as an exercise for you guys. Maybe you want to put it into a matrix and do row reduction, or maybe you just want to put the coefficient matrix here, find the inverse, and multiply it by the vector W1, W2. But however you do it, you should find that you get that t of v1 equals 5/11 w1 plus 2/11 w2, and that's like our x, and t of v2, which is like our y, equals 3/11 v1 minus 1/11, sorry, w1 minus 1/11 w2. So because we know a linear combination of v1 and v2 that gives us w1, and a linear combination of v1 and v2 that gives us w2, we can use our linear algebra knowledge to solve for a linear combination of w1 and w2s that give us both t of v1 and t of v2. Let's do one more example just to make sure we know what's going on here. So let's have our field of scalars be just the real numbers. So let's have our linear transformation. I'll still call it t. And let's say we go from vectors in R2 to 2x2 matrices. And let me tell you what this linear transformation does. So let's say that it takes the vector AB and it outputs the following matrix. So it outputs the matrix where the first column is A, B, and the second column is B minus A. So for example, if I wanted to take the transformation of the vector 3, -1, then this would give me the matrix 3, -1, -1, -3. So that's how this transformation works. Let's first show that this is indeed linear. That's something that we should do. So let's show that this is linear. So remember, to show that something is linear, we need two things. We need to show that we can split it apart across addition, and we need to show that we can take scalars out. So let's do the first one. Let's show that we can split it apart across addition. So let's, first of all, figure out what the transformation of two vectors added together is. So here's AB, and here's the second vector, CD. So that's going to be the same thing as the transformation of, well, we know how to add vectors. We just add entry-wise, so A plus C, B plus D. So there's our vector. And what does our transformation do? It creates a 2x2 matrix where the first column is the same thing, A plus C, B plus D. And the second column is reversing the top and bottom entry and negating in the lower right corner. So this becomes B plus D and a negative A plus C, which is negative A minus C. So that's what happens if we add and then transform. Let's do it the other way. Let's transform first and then add. So we'll transform the vectors AB and CD first, and then we'll add them. So I know what these are. So remember, the transformation takes these vectors and it creates the following matrix out of them. So we need to add these. It'll be C, D, D minus C. And now we just add entry-wise. So we get A plus C, B plus D, B plus D, and negative A minus C. So we see indeed both ways that we do it, we end up with the same answer. So it is linear under vector addition. Now let's do scalar multiplication. So let's do the same thing. So let's do the second part. So if we take the transformation of, let's call the scalar S. So S times AB. Remember, S is just some real number. And we know how to scale a vector. We just multiply each entry by that scalar. So this is the same thing as T of SA SB. And we know how the transformation works. We get the following 2x2 matrix out of it. So we get SA, SB, and then SB negative SA. Great. So let's do the other way. Let's show that we get the same thing if we transform first and then we scale. And you should see that this is going to be fairly straightforward. This is the same thing as S times A, B, B minus A, but we know how to scale matrices. We just multiply every entry by that scalar S, so we get S, A, S, B, S, B, S, or sorry, negative S, A. I mean, alternatively, we also could have just kind of went backwards here. So we could have went from this matrix and then factored out that S here, and then noticed that this is the same thing as S times the transformation of the vector AB. So both ways do it. We can either show that both things give you the same answer, or you can just do it in one string of equalities. So we go here, then here, then here, then here, then here. And for part one, the addition, that would work the same way. So instead of doing it two ways, we could have done it in one long string. We could have went from here, and we could have noticed that it is indeed these two matrices added together here. And then notice that that is just the transformation of AB plus the transformation of CD. Both things are literally the same work. It's just two different ways of writing it. And what's nice here is that, well, we know a basis for R2. So R2 has the basis. So we'll say call it B. So that has the basis 1, 0, 0, 1. So we can write the transformation. So T of AB. Well, we can view this AB as a linear combination of 1, 0, and 0, 1. So that is T of A times 1, 0 plus B times 0, 1. For example, if this vector maybe was 2, 3, this would be 2 times 1, 0 plus 3 times 0, 1. And then using our ideas of splitting apart linear combinations, we can view this as A times T of 1, 0 plus B times T of 0, 1. And we know what T of 1, 0 is. We can work that out. That's A of, well, it's going to be the matrix 1, 0, 0, negative 1. And the transformation of 0, 1 is going to be 0, 1, 1, negative 0, which is just 0. Oh, actually, this T shouldn't be here. I don't know why I wrote that. Let me get rid of that there. So it's just B times that matrix. Because remember, we already took the transformation. We already turned this into a vector in 2 by 2 matrices, and it gets turned into this vector by the way we defined it. So that's how this linear transformation works. The last example should have gave you a hint about this. But a really important property of linear transformations is that basically, as long as you know what happens to basis vectors under the linear transformation, you know what happens to all vectors under the linear transformation. So that's really key. All you need to know is where the basis vectors get mapped to, and then you know where every other vector gets mapped to. And that makes sense, because remember, with a basis is a set of vectors where you can uniquely represent all other vectors as a linear combination of those basis vectors. We'll show this result for a spanning set, but usually we'll apply it to a basis, because the spanning sets that we care about the most are bases. And the whole idea is, if we have two linear transformations, we'll call them T1 and T2, and they agree on every vector in a spanning set, you can think basis if you like. So T1 of VI equals T2 of VI for every vector in your set. That means that T1 of any vector is the same thing as T2 of that vector. So they agree on every vector. If they agree on a spanning set, then they agree on every vector. So let's go ahead and show this. So let's just take some vector v and apply both T1 and T2 to them, and we want to show that we get the same thing. And we're allowed to use the fact that for any vectors in our spanning set, that T1 of Vi equals T2 of Vi. So remember, if we have a spanning set, we can always write any vector as a linear combination of the vectors in a spanning set. And if the spanning set is a basis, it's a unique way of representing the vector. So let's go ahead and do it. So consider, so let V be, let's call it A1 V1 plus A2 V2 all the way to AN Vn. So we wrote V as a linear combination of the vectors in our spanning set. And again, if our spanning set is a basis, if it's linearly independent, there's only one way of doing it. And if it's not a basis, that's fine too. We can still do it, it's just not unique. So let's go ahead and let's apply T1 and T2 to it. So let's take T1 of V. Let me scroll to make a little more room here. So T1 of V is going to be T1 of A1 V1 plus A2 V2 all the way to AN Vn. And then we can use theorem 6.1 here, and we can separate this linear combination into its component parts. So this is going to be A1 times T of V1 plus A2 times T, T1 of V1, T1 of V2, all the way to AN times T1 of Vn. But remember, I know that T1 of each vector in my spanning set equals T2 of each vector in my spanning set, so let me use that. I know that we have A1, well, we have T1 of V1. V1's in my spanning set, so this is going to be T2 of V1 plus A2 T2 of V2 all the way to AN times T2 of Vn. And that's because T1 of V1 equals T2 of V1. T1 of V2 equals T2 of V2. And T1 of Vn equals T2 of Vn. And for all the other vectors in there as well. So we're using our assumption here. And then we can just use linearity again. So this is just T2 of A1 V1 plus A2 V2 all the way to AN Vn, just using the transformation of a linear combination property, theorem 6.1. And, well, what is that? That's just T2 of V. So we did it. We showed that T1 of V equals T2 of V. And the thing that we had to use was, once we separated this into a linear combination, that T1 of V1 equal T2 of V1, and the same thing for all the other vectors in our spanning set. So using that, we were able to write T1 of V in the same way as T2 of V, so these guys equal. So, remember that a basis is special in that it's a spanning set and it's a linearly independent, which means that every vector can be written, because of the spanning set, it can be written as a linear combination of the vectors in your basis, but because the basis is linearly independent, that it could be written uniquely as a linear combination of vectors in your basis. Because it's a basis, there's only one way of writing a vector as a linear combination. And a natural question to arise is, well, if we do have a basis in V, let's say we have a linear transformation T, and it goes from V to W, and let's say we have some basis of V, whatever, let's call it B1 all the way to Bn. In order for something to be a linear transformation, is there any restrictions on what we can send these vectors to? Do we need to be careful about where we send each of these basis vectors? And the answer indeed is no. In fact, everything just behaves extremely nicely. Linear transformations are about as nice as it gets. So let's look at this little theorem, theorem 6.3, that basically says that. So let's say we indeed do have a basis of V, we'll call it B1 to Bn, and let's say that we have n other vectors, this time in W, and I should say that this is indeed a set of possibly non-distinct vectors in W. And the way I'm thinking about it is I'm thinking of these W1s. I want these guys here to stand in for where each B gets mapped. So I want W1 to be kind of T of B1. Maybe a diagram would kind of help here. If V was this vector space and W was this vector space, and here's my first vector in my basis, we'll call it B1. Then my transformation, which we'll call T, maps B1 to T of B1, which I just call W1. That's how I'm thinking about this. Okay, so now that we have those vectors, what I'm saying is there's a unique linear transformation that sends Bi to those Wi's. And where does it send any vector V? Well, it sends V to the transformation of V via where it sends the basis vectors. So let's show that on the next slide. And in fact, there's not a lot to say for this. It's just fairly straightforward. So if we have a vector V written as a linear combination of our basis vectors here, well, we know our AIs are unique since our B's are a basis and we're writing V as a linear combination of our basis vectors. So if I apply T to V, I can split that apart into A T of B1, or sorry, A1 T of B1 plus A2 T of B2, all the way to AN T of Bn. And we know that if we have a linear transformation where T of Bi gets sent to Wi, so B1 gets sent to W1, B2 gets sent to W2, etc., we know this exists. And by the previous theorem, if there were two transformations that sent B1 to W1, B2 to W2, etc., they have to be the same transformation. So this transformation is indeed unique. So we're good to go there. So in short, basically, we can totally describe any linear transformation by where it sends the basis vectors, and those basis vectors can be sent to any vector. So that's kind of the takeaway here, is we can, so T is completely described by where it sends the basis vectors, and there's no restriction on what T of bi can be. So any basis vector can get sent to any vector in W that you like. And any choice of the image of basis vectors gives you a new linear transformation. So the last thing we'll do is we'll look at an example here that goes from the vector space of polynomials of degree 3 or less to three-dimensional vectors. And we know the following things about this transformation. And indeed, I will tell you, you can check if you like, but I will tell you that these vectors are a basis: 1, 1 plus x, 1 plus x squared, and 1 plus x squared plus x cubed. They are indeed a basis for polynomials of degree 3 or less, P3. And I'll tell you where these basis vectors go. So 1 goes to the vector 1, 0, negative 1 in R3 in our output set. 1 plus x goes to 0, 1, 1. 1 plus x squared goes to negative 1, 1, 0. And 1 plus x squared plus x cubed goes to 0, 0, 1. And I want to know what linear transformation does this. This kind of defines it, but what does this look like for an arbitrary polynomial? Where does that get sent? So maybe pause the video and see if you can figure this out. Where is this vector in P3, this third degree polynomial, where is this going to get sent in R3? Okay, so now that we're back, one thing that I'll note is that, well, I can easily get these separate parts of the constant part, the linear part, the squared part, and the cubed part just from taking linear combinations of these four vectors. Well, the constant part is easy. There's 1, so it's just C0 times 1. For the next part, I noticed that x is just 1 plus x minus 1. And similarly, x squared is this guy minus this guy, the one before it. And x cubed is this guy minus this guy. And then we can use the properties of linear transformations to help us out here. So let's go ahead and write this down. So I'm going to write that p of x here is the same thing as C0 times 1 plus C1 times 1 plus x minus 1 plus C2 of 1 plus x squared minus 1 plus x. And we still need the last one, so we need C3 of 1 plus x squared plus x cubed minus 1 plus x squared. Okay, so that's great. Now, let's apply our transformation to this and then split things apart. So the transformation of p of x is going to be, so it's going to be C0 times the transformation of 1, which we know, plus C1 times the transformation of 1 plus x minus 1, which I'll write as 1 plus x minus the transformation of 1. Just splitting that apart there using the linearity of our linear transformation, plus c2 times the transformation of 1 plus x squared minus the transformation of 1 plus x. And finally, plus c3 times the transformation of 1 plus x squared plus x cubed minus the transformation of 1 plus x squared. And the nice thing is, we were given these things here, so we can just plug these in and work it out. So let's go ahead and remind ourselves of what these are. So t1 is 1, 0, minus 1. 1 plus x is 0, 1, 1. So let's plug them in. In fact, let's write that, just so we don't have to keep scrolling up. T of 1 is 1, 0, minus 1. T of 1 plus x was 0, 1, 1. T of 1 plus x squared was negative 1, 1, 0. And finally, t of 1 plus x squared plus x cubed was 0, 0, 1. So let's put that in. There we go. So we'll go back to the red pen here. So this is going to be C0 times T of 1, which we know is 1, 0, negative 1, plus C2 of 1 plus x is 0, 1, 1, minus 1, which is 1, 0, minus 1, plus C3 of t of 1 plus x squared, which is negative 1, 1, 0, minus t of 1 plus x, which is 0, 1, 1. And then finally, let me give myself a little more room here. This should be C1 and C2, and this will be C3 of 1 plus x squared plus x cubed is 0, 0, 1, minus 1 plus x squared, which is negative 1, 1, 0. So now we just have to work this out. So this is going to be C1 times 1, 0, negative 1. So that's no problem. Plus C1 times 0, 1, 1 minus 1, 0, negative 1. So this is negative 1, 1, 2 plus C2 times, well, negative 1, 1, 0 minus 0, 1, 1 is negative 1, 0, negative 1. And C3 times 0, 0, 1 minus negative 1, 1, 0. So that's going to be 1 minus 1, 1. And then let's just clean this up and put this into one vector. So let's go ahead and do this. All right. So this equals, well, let's do the top vector, or the top entry of our vector first. So we have a C1, or sorry, this should be a C0. We have 1 C0 minus 1 C1s minus 1 C2s and 1 C3. So that's going to be C0 minus C1 minus C2 plus C3. That's the first entry. The second entry is going to be, well, there's only C1 and C3, so it's going to be C1 minus C3. And the last entry is going to be negative C0 plus 2C1s minus 1C2 plus 1C3. So that's what this linear transformation does to any polynomial. So for example, and this will be the last thing, so let's say we take the transformation of, let's say we have what, negative 1 minus x plus 2x cubed. So there's no x squared term. So here we have that C0 is negative 1, C1 is negative 1, C2 is 0, and C3 is 2. So this is going to be, well, C0 is negative 1 minus negative 1 minus 0 plus 2 is the first thing. Then we have C1, negative 1 minus C3, so minus 2. And here we have negative C0, so that's plus 1 plus 2 times C1, so that's minus 1, minus C2, so minus 0, plus C3, which is 2. And then we just simplify that. So here we have negative 1 plus 1 is 0, minus 0 plus 2 is 2. Negative 1 minus 2 is minus 3. And 1 minus 2 plus 2 is 1. So this transformation sends this polynomial, negative 1 minus x plus 2x cubed, to the vector 2, 3, 1.